chapter 17, which starts with common ion effect. And the common ion effect is important because it deals with buffers. If you're going to learn a topic in chemistry, in acid-base chemistry, that is, buffers are it, because they are so common. Whenever, if you're in the biological field or even the pharmaceutical field, things need to be buffered. That way the pH doesn't change under different conditions. And so that's what we're seeing here. And again, there's always shortcuts that you guys can apply. And it's first understanding the chemistry and then realizing how the shortcut equation is derived from the chemistry. So I see some people still trying to get admitted, so I'll just have them join. Okay, I think I got everybody now. There's no one in the wait list. So as I was saying, I'm still grading your quiz too, and I will release that probably tomorrow. I'm trying to make sure that everything's okay. And you'll probably find mistakes, and if you do, in terms of my grading, I'm sure you'll let me know, and I'll be more than happy to give you credit if I made a mistake. But we're going to be wrapping up acid-base chemistry this week. And next week, we don't have any lecture schedule because we're just going to be working. You guys are going to be taking the midterm exam, which will be given in 2 parts, just because I don't want to have you guys take one long exam. And it's only going to be the first half up to acid-base chemistry. So let me just see. So let me go ahead and get started in this particular discussion so that I can get by. And for those of you in lab, you can do the activity. So go ahead. So we're looking at the common ion effect. And you guys already know about the common ion. That's when you have some chemical, let's say that you have some ionic substance, and then it breaks up into water, but it has this, but you introduce this ion via a secondary reaction, let's say sodium A, where this might be fluoride, sodium fluoride, and this might be something like barium fluoride. So we did this particular common ion effect at the end of chapter 16. And you guys remember that when you have a common ion in the initial line, you're going to include concentrations for the chemical that's doing the chemistry, and then the chemical that has been introduced to that solution. And that's your common ion. In acid-base chemistry, when you have a common ion effect, you also have something called a buffer. Acetic acid dissolving. And the question is, what is the percent of acetic acid when you put it in solution? And the answer is just going to be based on the Ka of acetic acid and the initial concentration of acetic acid. And acetic acid, we usually shorthand it as a hydrogen and the acetate ion. So what you can do is, just based on what we've talked about so far, you can go just calculate the hydronium ion concentration, and that's just equal to the Ka times the initial concentration of acetic acid. And in this particular case, I tell you that the acetic acid initial concentration is 0.1. And so if you do this equation right here, which you guys should all be experts on, then you're going to find out that the hydronium ion concentration is 1.34 times 10 to the minus 3, and that the pH is going to be 2.87. Okay, so if the question is what is the percent ionization alpha, then that's going to be equal to the amount of acid that forms, that's X in the ice table, divided by the initial concentration of the acid. And so that's just 1.34 times 10 to the minus 3 divided by 0.10. And so that's this part right here. And if you multiply that by 100, what you get is 1.34%. Now, why is this important? Because I want to show you that acetic acid has a percent dissociation of about a little bit more than 1%. 1%. Okay. Now, what happens when you introduce the common ion? The common ion is, let me clear this real quick, is now, let's say that I have a beaker and I put acetic acid in here, and the acetic acid concentration is 0.100, but I also put in here sodium acetate. So the sodium is a spectator, but the acetate now comes in as a common ion to acetic acid. So that's what we have in the second part. We have acetic acid, that concentration is 0.1, but let's say that I put sodium acetate and that particular concentration is also 0.1. So in this initial line right here, you have to put 0.1, because in your beaker of water, you not only have hydrogen ion or acetate ion, and this comes from the acetic acid, which was 0.100 molar, but you also introduce in here acetate ions from the sodium acetate, and that's 0.100. So that's why you have to put initial concentrations for both of these. The next thing that you need to do is realize that, okay, the acid is going to dissociate, because that's what acid does in water. It dissociates and it produces hydrogen. So this has to be minus X. Let me clear this for you. This has to be minus X right here. This has to be minus X. We don't really worry about water because water is never introduced into the mass action expression. This is plus X and this is plus X. So what you have is the following. Ka is equal to the hydronium ion concentration times the acetate ion concentration all over the initial concentration of the acetic acid. Now this is going to be 0.100 minus X. This right here is what you are calculating. This right here is 0.100 plus X. Okay, that's what you see right there. So when you solve this whole thing, and of course we know what that is, we solve this as hydronium is equal to, let me clear this real quick. Okay. Hydronium is equal to the following. It's equal to Ka times HAC all over AC. But remember, this is 0.1 minus X, and this is 0.1 plus X. But we can make the simplifying assumption method and say that X is negligible for both of these. We can say that X is negligible. So what happens is that this becomes 0.1, this becomes 0.1 right here. And so hydronium is just Ka right here, because we have a common ion, and the common ion will basically simplify the math. And so if the hydronium is 1.8 times 10 to the minus 5, which is our Ka value, then if we take the negative log of that number, then what we get is we get a pH of 4.74. That's basically how we would do that. Again, you can see that here, when the concentration of both the acid and its common ion are equal, then the hydronium is just equal to the Ka. That's something that you guys should remember, especially for the lab that you guys are going to be doing next week. Okay, and then if we calculate the percent ionization, then what we have is 1.8 times 10 to the minus 5 divided by the initial concentration of the acid, and that number is 0.018%. So with common ion, the alpha is 0.018%. With no common ion, the alpha is 1.34%. So what I'm saying here is that this is consistent with Le Chatelier's principle, because if we look at this equation right here, what we're doing is we're taking an acid and we're causing it to dissociate, but now we introduce a common ion and it's going to force the equilibrium to the left according to Le Chatelier's principle. If you have more products, then the reaction will offset the equilibrium by converting this product right here to reactant. And so what that means is that less of the acid is going to produce its conjugate. The reaction is going to be less favorable to the right. So keep this in mind, because what's going to happen is that you guys are going to see that this is important in terms of buffers, because what we have here is something called a buffer. Okay. So this is the conclusion. Ionization decreases the presence of a common ion. So let's take a look at this other problem. Consider the previous problem in a common ion. This is already what we solved. And what I want to show you here, excuse my flash news bulletin on my iPad. I need to turn that off, but I'll do that after this class. Here is what we just solved. Now, the reason why I'm showing it again is because I want you guys to see, I want you guys to see our derivation. Remember that from all of this, we said that the hydronium ion concentration was equal to the Ka times the conjugate base over the acid. Okay. So that's the acetate ion. That's the, goes back to this right here. Ka equals hydronium. Okay, I got that backwards. This, let me erase that real quick. Sorry. The hydronium is going to be equal to the acid that we start with times the Ka over the conjugate right here. That's the equation that we have. Now, mostly the problem in acid-base chemistry is to calculate the pH. And the pH is the negative log of the hydronium ion concentration. So what if we take the negative log of all of these? Okay, what we'll see is that we have the negative log of the hydronium equals the negative log of Ka HAC O over AC minus. Now, what I want to do is I want to simplify this. I'm going to erase this right here. Okay, apologize for that. I need some board space. So this is somewhat important, because what I can do here is that this value right here is just the pH. And this value right here is just equal to the pKa. And so if we take the negative log of that term, that's going to be minus the log of HAC over AC. Okay. So what we're going to do is we're going to simplify this even further and make this a plus. And the way we make that a plus is we say that we're just going to inverse this ratio right here. And why am I doing this? I'm doing this because we're going to derive a very, very famous equation that you guys will need to know how to use. And this equation right here, which, by the way, the chemistry is embedded in the ICE table. This right here comes from doing the mass action expression and then taking the negative log of all the terms. This right here is the Henderson Hasselbalch equation. And that's an equation that you should know, especially if you're going to take the MCAT, because this tells you what the pH of your solution is. If you know first the identity of the acid, so you can look up the Ka, and you know the concentration of the conjugate pairs. And that's what we see in this derivation right here. Okay, that's what we see in this derivation right here. Basically, this right here is what I just derived. This is the Henderson-Hasselbalch equation. And remember that the log term is always the conjugate base over the conjugate acid. That's the log term. So if we go back to our previous problem where we had both 0.10 molar sodium acetate and 0.10 molar acetic acid, and we plug it into this Henderson-Hasselbalch equation, you can see that I didn't even have to do an ice table. All I had to do was plug it in here and say that the hydronium ion concentration is equal to the pKa of acetic acid. And the pKa of acetic acid is the negative log of 1.8 times 10 to the minus 5 plus the log of the base over the acid. And this was 0.10 molar, and this was 0.10 molar. And so the log of 1 is equal to 0. So the hydronium ion concentration, sorry, not the hydronium ion concentration, but the pH here, this is the pH, is equal to the pKa. That's what the Henderson-Hasselbalch equation gives you. It gives you a shortcut of doing common ion effect. And you want to remember this because why work through the ice table when someone already has figured it out for you, okay? So that's very important, especially for the lab this week. So let me go ahead and clear this, okay? And then move on. That's the pH Henderson-Hasselbalch equation and the pOH Henderson-Hasselbalch equation. In the pOH, you need the pKb of the base. And here, instead of the base over the acid, it's the acid over the base. Okay, so please keep that in mind. It's the inverse of the pH equation. So pH of a solution can be calculated using this powerful Henderson-Hasselbalch equation. Okay, and again, I want to stress that the Henderson-Hasselbalch equation has its roots in the ice table, and the ice table tells you how the chemistry is being run for that particular species. So don't just write or use the Henderson-Hasselbalch equation unknowing what that equation means, because if you just take it blindly, then you're just going to start using it in wrong circumstance. Always remember that it comes from the mass action expression and that you're taking the negative log of all the terms in the mass action expression. And in that mass action expression, you're solving for the hydronium ion concentration or the pH.
Professor?
Yes.
Can it only be used for weak acids and weak bases because
Yes.
they have conjugates?
Exactly. Good point. It can only be used for weak acids and weak base. That's a great question, because remember, when a weak acid converts over to its base, then the base can also convert back to its conjugate. In a strong acid situation, you never have a common ion. So if I gave you something like HCl and NaCl in the solution, and you said, oh yeah, there's my acid and there's my common ion, you're going to be going down the wrong path, because as a strong acid, there's only one direction for this species to occur. It's always going to give you H plus and Cl minus. It's never going to go back in the reverse direction, because the chloride doesn't want to grab a hydrogen in order to form the strong acid, because by definition, a strong acid will always stay dissociated. So this is only a one-way street, and because it's a one-way street, you can't ever have a buffer. So again, it pays to remember our 7 strong acids, because then you remember that those things can't create buffer solutions. It has to be made from solutions that are conjugate pairs, that are weak acids or weak base. And then let me go back a little bit, okay? And the reason why I want to go back is because you see this right here? That's the Ka of acetic acid. And when you take the negative log of that, you got 4.74, I believe. Well, when you're creating a buffer, remember you guys use buffers in lab. You use the buffer solution to calibrate the pH probe at 4, and then the higher end you would use the buffer solution at 10. Well, these buffer solutions are important because maybe you have an experiment in which the pH needs to stay consistent. Well, you need to make sure that you form the right buffer. You have to prepare that. And usually the buffer, let's say you're shooting for pH of about 5. Well, the acetic acid acetate ion would be a great buffer combination because its pKa is very close to 5. So when you're preparing a buffer solution, you want to look for chemicals that have conjugate pairs and that the Ka value is very close to the pH that you are shooting for. Okay. And if you can figure that out, then it'll be much easier for you to prepare buffer solutions. And even though 4.74 and 5 are not identical, you can adjust the concentration of the acetate ion and the acetic acid, this ratio right here, so that this value becomes 5. Okay, that's the whole concepts of buffer solutions. Buffer solutions are so important in science, especially biological science, and the technician needs to know how to prepare them. Anyway, let me go ahead and move on from this. Here's a question that, again, we're using the Henderson-Hasselbalch equation. This is basically what I just derived right here. And just using the Henderson-Hasselbalch equation, we bypass the mass action expression. We just go straight to the Henderson-Hasselbalch equation and we get our answer. Okay. So here's another question, and this one is a little bit more involved, but it still deals with buffer. Here we have a buffer. We have the acetate. Remember, acetate is the anion. This is acetic acid right here, CH3, C double bond O, OH. The acetate ion is basically all of this except the hydrogen. This is the ionized hydrogen. That's the hydrogen that comes off. So that's acetate. CH3COO minus. It's got a negative charge. Acetic acid would be represented in that way. That right there is this hydrogen right there and the acetate ion. So we're going to use shorthand notation a lot just because you don't want to constantly write this structure for acetic acid. Here we have a buffer situation. We said that the acetate ion, AC minus, is 0.100 molar, and that the acetic acid is 0.200 molar. The Ka we know is based on acetic acid. And what is the pH of the buffer? Well, that's pretty easy. pH is equal to 4.74 plus the log. Remember, it's the base, conjugate base over the conjugate acid. So the base is going to be 0.100 over 0.200. So this is just the log of 0.5. And if you take the log of 0.5 and put that in your calculator, that term goes to, let me just do this real quick. That term goes to negative 0.301. So if you take 4.74 and you subtract 0.301 from that, we have a pH of 4.439. That would be the pH of that particular solution. So let's see if we have that. Okay, let me go ahead and clear this so that you guys can see. So you can see that, again, the Henderson-Hasselbalch equation provides you a shortcut right here. Okay, and you see how this value now is sort of offset from 4.74. In fact, it's lower. And it's lower, again, just based on the fact, you guys know the chemistry. You have acetic acid, you have the acetate ion, and the acetate ion is much higher, is 0.10 molar, and the acetic acid is zero point 0.2. So what's going to happen, of course, is that the the um, the ratio here is going to be such that this solution is going to be more acidic than usual. If these two were the same concentration, if this and this were the same concentration, you would get a pH of 4.74. But because the acetate ion is lower in concentration than the acetic acid, the reaction is going to be loaded in reactant. It's going to go more favorably in the forward direction. More favorably in the forward direction means that you generate more hydronium. More hydronium means you have a lower pH, which is reflected in 4.44 versus 4.74. Okay, so just based on what we've talked about in terms of Le Chatelier's principle, it should be you should be able to understand why the pH is lowered. Okay, so let me go ahead and clear this out. The second part of this is calculate the initial pH, the final pH, and the change in pH that results from 1 milliliters of 0.1 molar hydrochloric acid added to this solution. Um, so what we're going to do, this is this part right here, second part, okay? This is a problem that will take a little bit of explaining, so please bear with me, okay? What we have is acetic acid initially. That's our initial. Then what we're going to do in here is we're going to add hydrochloric acid. And hydrochloric acid and the acetic acid, of course, will mean that you're going to have the acetate ion and some other product. But if let me try and draw you a beaker so that you can visualize what's going on. We have acetic acid, we have the acetate ion. This comes from sodium acetate. This comes from just regular acetic acid. And then we're adding to this solution, according to this problem, 1 milliliter of hydrochloric acid. Now the question I have for you is, hydrochloric acid, which is going to produce hydronium, so you have a hydronium ion from hydrochloric acid, which is it going to react with? What would you say? Would it react with another acid and form H2AC? Or do you think it'll react with a base and form the acetic acid? You guys already know this, okay? You guys know that an acid is not going to react with another acid. In fact, an acid is competing against that other acid. It'll most likely attack the base. So this is not the equation you want to write. This is not the equation you want to write. The equation that you do want to write is the following. You have the acetate ion plus hydrogen ion goes to acetic acid. That's the equation you want to write. And this first part right here is stoichiometry. Because whenever you have a strong acid or a strong base, those are the chemicals that are going to dictate how this show is going to be run. A strong acid will always demand that whatever base is present, that base take on the hydrogen. Okay, so hydrochloric acid will always dictate that all the acetate consumes the H plus from HCl. So what you have to do is you first solve the stoichiometry. Okay, this is what's different from what we've been talking about before, is that you guys are going to first have to solve the stoichiometry, and then from the stoichiometry you need to figure out how much acetic acid remains and how much acetate ions remains. And then from this concentration at the end, you can either put it in the ice table or you can directly go to the Henderson-Hasselbalch equation. Okay, so hold on to that thought. Remember this picture. You have a beaker of water, you've got acetic acid in here, you've got acetate ion in here, you're adding hydrochloric acid in here. The hydrochloric acid is going to attack the acetate ion. So this is what's going to happen. You've got acetate ion plus hydrogen ion goes to acetic acid. And this is, again, what I said was stoichiometry. Remember, when you do stoichiometry, you have to deal with moles, not molarity. We don't deal with molarity until we get to equilibrium. In stoichiometry, we deal with moles because, remember, depending on the limiting reagent, all the chemical gets consumed. So the question, I'm going to start here with start. So we're using the term S. We need to figure out the moles of the acetate ion. The moles of the acetate ion is, we have here 0.2 molar, 0.1 molar acetate, and it tells me that I have 100 milliliter of this buffer solution. So if I have 0.100 moles per liter, and I have 100 milliliters, I'm also going to introduce a new concept to you guys called millimoles. And the reason why I want to introduce millimoles is because we usually deal with milliliters. So rather than convert something from milliliters to liters and then reconvert it in the back end, we're just going to use milli. So when you have 0.1 times 100, then that right there is 10.0 millimoles, or 10.0 times 10 to the minus 3. Okay, so our start of the acetate ion is 10.0 millimoles. Our acetic acid is 0.2 times 100, and so that will be 20 millimoles. Okay, our hydrogen ion concentration, we have 0.1, and what we're doing is we're introducing 1 milliliter of that. So that's just 0.1 millimoles. So that's our starting chemicals. Then the reaction is going to be based on the limiting reagent. The limiting reagent is my hydrogen ion. It's going to be 0.1 minus 0.1 millimoles, minus 0.1 millimoles, plus 0.1 millimoles, because it's going to be stoichiometric. It's going to be based on the limiting reagent. Okay, so 10 minus 0.1, because 0.1 of the 10 is going to be consumed, that's 9.9 millimoles. This is going to be 0 because all the acid gets consumed. And 20.0 plus 0.1 is 20.1 millimoles. Okay. So remember this, because I got to clean my screen again. Okay. Because these are the initial concentration of the chemicals that are going to be in my beaker. So what happens is that when all the acid reacts with the acetate ion, okay, the acetate ion will turn over to acetic acid, because the acid, the H plus, is going to react with that. And so this 10 will become 9.9. This 20 will become 20.1. So what we have now is common ions in the solution. So we can just go straight to the Henderson-Hasselbalch equation. pH is equal to the pKa of acetic acid, which is 4.74, plus, now we can see that our base is 9.9 millimoles over 101. And the question you might ask yourself is, where did I get 101? And I got 101 because I had 100 milliliters of buffer solution initially, and I'm adding 1 milliliter of hydrochloric acid. So 100 plus 1 is 101. And you see how this is milliliters? Millimoles and milliliters makes it moles per liter. That's why I like to use millimoles, because when you have a millimoles and you divide by a milliliter, it's like taking a moles divided by liters. And the bottom here, this is the conjugate base. Remember, the top is the conjugate base, and the bottom is the conjugate acid. That's 20.1 millimoles over 101 over 101. What you see here right away is that the 101 will cancel out. And so it's really just 9.9 over 20.1. And so if you do that, then what you will get is this term right here will simplify. And what you will get is the answer that you have for this problem. The okay, what happens is that for this second part right here, if you solve this math, and let me just show you that in this next line. Okay, right here, 9.9, 20.1, volume's 101. And we can put this in the Henderson-Hasselbalch equation. And what you see right here is the magical part about buffers, right there. Okay, so initially, when we just had the buffer, we had a pH of 4.44. When we contaminated with hydrochloric acid, and 1 milliliter contamination of hydrochloric acid is pretty high, okay? We contaminate this 100 milliliter buffer with 1 milliliter strong acid. Look where the pH turned to. It only went from 4.44 to 4.43. That's why these chemicals are called buffer, because they buffer the resistance of pH changes. When you have a buffer solution, what's going on is that the acid will get consumed by the conjugate. And so this acid is wiped out. So it doesn't change the pH of the solution. Yeah, you form more acid here, but that's not hydronium. And remember, hydronium is what influences pH changes, because the equation for pH is negative log of hydronium ion concentration. That's why buffers are really great. We went from an initial pH of 4.4, went to a final pH of 4.43. Our change is only 0.01. That's why when you guys use the buffer in lab, even if you contaminate it, that buffer solution should still pretty much stay within that region. If you have a buffer 4, it's going to deviate of plus or minus 0.05. Okay, if you contaminate it. If you have a pH 10, again, it'll deviate plus or minus 0.05, but it pretty much stays the same. That's why we like buffer solutions, because you can contaminate it and that pH is not going to change. So let me go ahead and talk to you about this part right here. Suppose I don't have a buffer solution. Suppose I just take 1 milliliter of hydrochloric acid and I put it into this water that's 100 milliliters, and it's not a buffer, it's just plain water. The question is, what is the pH of that water initially? Well, if it's pure water, the pH is 7. Okay, you guys don't need to pick up your calculator to figure that out. It's pure water, nothing's contaminated. We're assuming it's 25 degrees. The pH is going to be 7. Now we're going to be adding to this beaker 1 milliliter of 0.100 molar hydrochloric acid. And the question is, what's the pH of that solution? And you guys will know how to solve this, because this is really just a dilution problem. You're taking 1 milliliter of hydrochloric acid and you're putting it in 100 milliliter. So what's the new concentration? You guys can calculate this. You can say M1V1 equals M2V2, where V2 now is 101. M1 is 0.10 molar, and V1 is 1 milliliters. So this is our hydrochloric acid. This is the new solution that we're solving. And so you see that in this next problem right here. This is part 3. And again, it's not difficult to solve this problem if you know your chemistry. All you're doing is you're taking 100 milliliters of water and adding to that 1 milliliter of hydrochloric acid. That is 0.100 molar. So you're basically diluting that 1 milliliter of hydrochloric acid. So if you do that, again, we can do this dilution problem. M1V1 equals M2V2. Well, we're solving for the new concentration of the acid. And let me clear this for you. There is no reaction because there's no chemical in the water that's going to react with the hydronium. The hydronium is just going to go into solution. So that's what we see right here. We have 0.1. We're going to make that go with water. That concentration is going to go to 0.1 because it's 100% dissociation. Remember, that's a strong acid. The new volume is 101 milliliters. So the concentration of the acid is 0.100 molar over 101 milliliters, or 0.101 liters. Okay. What you can do now is, oops, I forgot. Let me go back. I made a mistake real quick. What we have is we have 1 milliliter of 0.100 molar hydrochloric acid. So the moles of hydrochloric acid is not point, well, basically it's the same thing. It's going to be 0.1. We can just do the M1V1 equals M2V2. And when we solve for M2, we come up with this concentration right here, 9.9 times 10 to the minus 4. And if we take the negative log of that, we get a pH of 3. What I want to illustrate here is that we had an initial pH of 7. Because it's not a buffered solution, we have a final pH of 3. So the difference in pH is -4. It dropped 4 pH unit because it wasn't buffered. Okay. So the whole take-home message here is that when you have a buffer solution, that solution is going to resist pH changes up to the buffer capacity. The buffer capacity is the concentration of the chemicals such that when it's all consumed, because it has to be consumed right here, let me go back. The buffer capacity is the following. This is removing hydronium. As long as this is present, any hydronium that comes into the solution will be consumed. And so if there's no hydronium that influences the solution directly, then there's no change on pH. And so the pH is maintained. That is, the solution is buffered. But as soon as this chemical is now consumed, suppose you add 10 millimoles of acid, what will happen now is that now this is totally consumed, and there you've exhausted your buffer capacity. There is no more conjugate base here to consume any more of the acid that's introduced. You've basically hit the buffer capacity of your solution. Okay, so that's a buffer capacity. So let me go ahead and move on here. This highlights the essential features of a buffer. The buffer, and we can go back to the Henderson-Hasselbalch equation, pKa plus the log, and this is for acid-base buffer, CD, conjugate base over the conjugate acid, base over acid. When you want to calculate the pH or even the hydronium ion concentration, because 10 to the minus pH gives you the hydronium ion concentration, you need to know the pKa of the acid. You need to know the pKa of that acid. And you know the pKa of that acid because it's just 10 to the minus Ka. And this is going to be found in a table somewhere. Whatever the equilibrium constant for the dissociation of that acid happens to be, that's your pKa. But this right here tells you that you have to have both conjugate pairs present. Depending on which one is greater, this value is going to be either positive or negative. It's either going to add to the pKa if it's positive, that is the base is higher in concentration than the acid, or it's going to remove from the pKa if it's negative, that is the acid is higher in concentration than the base. So that's basically what this Henderson-Hasselbalch equation offers. And usually this is good to, the buffer has an effective range of plus or minus one, plus or minus one. That's the effective range. So what you want to do, if you want to find chemicals that are going to be good buffers, you need to find it, the acid and its conjugate pair, and you want to find a pKa of that particular chemical. And if you're shooting for, like, say, pH of about 5, then your buffer range is going to be between 4 and 6. If you're shooting for a range of 10, then your buffer range will be 9 and 11. So a pKa of 10 to the minus 9 and 10 to the minus 11 will be the chemicals that you want. That's the Ka values that is going to make a good chemicals for these buffers. So that's basically what's going on right here. Again, this is the key ingredient of a buffer. The hydronium will get consumed by the conjugate. Okay, the conjugate now will convert over to the acid. That's why this drops and this goes up. If you have a base, the base will react with the acid will drop down, and the conjugate will go up. The whole idea of buffers is to remove these chemicals because these chemicals are responsible for pH and pOH. That's how buffer system works. And buffer system works in our blood. For those of you who've studied a little bit of medicine or in biology, you guys know that our blood pH has to be between 7.35 and 7.45. If it's below that, we have a term called acidosis. And acidosis simply means that our blood pH is mostly acidic. It's because it's dropped below 7.35. If we have a pH of our blood that's higher than that, we have alkalosis. Okay, so the buffer system in our blood is mostly dictated by proteins, phosphates. See how these are conjugate pairs? And then proteins are made out of amino acids. And because they have amino acids on them, when you remove the hydrogen from these amino acids, you have automatically the conjugate pairs. But most importantly, we also have the carbonates. The carbonates is the main buffer system in our body, right here. Okay, carbonic acid. So it's usually in a 10-to-1 ratio. We have in our blood system bicarbonate and carbonic acid. If we have too much acid in our body, it reacts with bicarbonate to form carbonic acid. If we have too much base in our body, then carbonic acid reacts with the hydroxide to give us water and the bicarbonate ion. So it's a great chemical in our system so that it regulates the hydroxide and the hydronium ion concentration. Okay, that's basically the buffer chemicals in our body. Now, again, like I said, if it drops below 7.35, we get acidosis. These are the symptoms: depression of the acute nervous system. You have fainting spells. You might go into coma, and then you will die if it gets too severe. Uh, what is the cause? Respiratory acidosis. That's because you have difficulty breathing. And if you have difficulty breathing, that means you don't expel the carbon dioxide out of your body. If you don't expel the carbon dioxide from your body, then basically this is the reaction that we have again. HCO3 minus goes to H2CO3. Bicarbonate, carbonic acid. Now, what happens if this reaction goes far to the right and we start loading up on carbonic acid? Well, our body has a natural way of getting excess of carbonic acid. We simply sweat it out and breathe it out. So if we get too much carbonic acid in our body, we breathe and we sweat right here. Okay? But suppose we have a difficult time breathing, so this channel is suppressed. What will happen, of course, is that if that channel is suppressed, then this whole equilibrium right here will start shifting to the left. And if you start shifting this equilibrium to the left, then you have a solution that is going to be more acidic, because what happens is that H2CO3 turns to bicarbonate and spits out a hydrogen in the process. That's why you have acidosis, because the carbonic acid is basically dissociating and putting more hydrogen ion in your system. So these are caused by pneumonia, asthma, or anything that diminishes carbon dioxide from leaving your lungs. And then we also have metabolic acidosis. That's where you remove natural acids from your body. If you are starving or fasting, then what you do is you start breaking down the fatty acids. And so again, you're removing acid, or heavy exercise, because then you have lactic acid. And then that basically means that there's going to be more acid in your body because you have a production of lactic acid. So this is the mechanism by which that occurs. Okay, and I already talked about that. In terms of alkalosis, that's when your blood pH goes higher than 7.45. That's because of the overstimulation of the central nervous system, um, muscle cramps, convulsion, and then you will die as well. What are the causes, or the causes of alkalosis? Heavy breathing. So what happens, of course, is that you that's a bad picture of somebody. Okay, uh, but if you breathe out, there's somebody's eyes right there. Okay, if you breathe out, then that basically means you're taking carbonic acid and you're converting it to carbon dioxide and water. So heavy breathing, and heavy breathing because you are hyperventilating, because you're afraid or hysteric, or maybe you have a fever. And so the question I usually had when I was a kid growing up was, someone is hysteric and they give him a paper bag to breathe in. And I was wondering why they did that. And the reason why they do that is because when they give them a paper bag to breathe in, then they're also breathing back their carbon dioxide that they are producing, thereby causing that, instead of removing the carbonate ion and causing this equilibrium to go to the right, because you're forming carbon dioxide, you're forcing it now to reverse this direction, and you're sort of helping yourself, so it will be more acidic, and so the blood pH will start decreasing. So that's why when you see people that are hysteric and they're breathing in a paper bag, it's because they don't want to hyperventilate. They need that carbon dioxide. And then of course there's also metabolic alkalosis. And metabolic alkalosis, again, is removing excess acid from your body, so your system becomes more basic. And that might be someone who's bulimic, or just throwing up excess vomiting. So these are the mechanisms. Okay. So buffer plays an important role in everyone, not only in the chemistry lab, but also for our health. So again, this is the mechanism. Buffer works because they are conjugate pairs. And the conjugate pairs in one end can react with the acid, or in the other end react with a base. And what it does is it really removes these chemicals which are responsible for pH and pOH. And by doing that, okay, then the pH of that system is maintained. So this is more specifically the mechanism by which hydronium is changed over to something else other than hydronium, or hydroxide is changed over to something other than hydroxide. Because remember, the pH of the solution is through these chemicals right here. Any changes on that directly changes the pH of the solution. These guys right here, they're not in the negative log hydronium ion concentration. These guys right here are okay to be formed because they contribute to the hydronium ion concentration indirectly. It's not a direct contribution. So that's basically it. So this is a summary of all the equations that I sort of talked about in this particular part. Okay. And you guys can just take a look at that. And I hope that part, and then I'll go ahead and talk about the next part because the next part is pretty straightforward. And that way I just have one class meeting Wednesday to talk to you about the bulk of chapter 17. That is titrations of weak acids or weak base with a titrant.